Hello. In this video, we are going to continue our study of concurrent lines in a triangle. So let's start by summarizing our previous findings. You may recall that we have used certain functions to prove that some lines were concurrent in a triangle. I will call this function a two function. More precisely, a two function is a map which takes as an argument a triangle ABC in a certain order, so it's an ordered triple of points, and the value fabc is a function defined on the plane and with real values. So a two function is a map from the triple of points to the real functions defined on the plane. And we are interested in functions like this, such that the zero set is a line, which I call LABC. So fabc is a function which is not necessarily an affine function, but we require its zero set to be a line. It's not necessarily an affine function. We have already met examples where fabc is some distance, so it won't be linear, it won't be affine. We will say that such a two function is cyclic if the sum of the cyclic permutations of fabc is zero. It's the zero function. And we used this very elementary fact that I will call a trivial, with a spelling problem here. It's the trivial lemma, which goes like this. If f is cyclic, so if f has this property, then the lines LABC, LBCA, and LCAB are parallel or concurrent. Well, it's really simple, because if a point M belongs to the zero set of two of them, it must belong to the zero set of the third. This is the principle we used to prove that the classical lines, such as the medians, perpendicular bisectors, etc., are concurrent. But we also noticed that very often these two functions are defined thanks to simpler functions which depend only on 2 points. So let's call G such a map. So G takes a pair of points, distant points, x, y, and gxy is a function defined on the plane. And with such G, we define delta G, which is a two function. So delta G depends on 3 points, ABC, and delta G ABC is just GAC minus GBC. If f is of this form, if f is of the form delta G, we will say that f is exact. So, of course, this terminology I use here is inspired by homology, because maybe you will agree with me that this whole thing has some sort of homological flavor. But I must admit I could not follow this trail very far. Maybe I'm not smart enough, or maybe this is a false lead. But I kept the idea, so I used this analogy to name the object. So fabc is called a two function because it's reminiscent of a two cocycle. Anyway, there is a second trivial lemma, which is that if f is exact and it comes from a symmetric G, that is a G such that gxy equals gyx, or if G is independent from y, then in both cases f will be cyclic. And this is exactly what happened in the classical case. We found a cyclic two function in each classical case, and every time it was an exact two function, except for the medians, where, if you recall, we have used the barycentric coordinates to define f, and because of this, since the barycentric coordinates depends on ABC with the order, and the order of ABC is important, we cannot say that f is exact. The function we used in that case were not exact, but it was not exact, but it was the only case. So now we would like to know if we can go further and use this new setup to prove that some other lines beyond the classical case are concurrent. So let's first talk about the Napoléon lines. So to define them, first consider a triangle ABC, and on each side you build an equilateral triangle. So A, that you call here on the side AB, I call gamma, a point such that AB gamma is equilateral, and similarly A beta C and alpha BC, where alpha is somewhere down below, they are equilateral triangles. For each of these equilateral triangle, consider its centroid. So let's call G gamma the centroid of this equilateral triangle, and so on. Then, if you draw a line from the opposite vertex of the triangle ABC to the centroid of the equilateral triangle built on one of its sides, you obtain three lines which happen to be concurrent at a point which is called the Napoléon point, because sometimes this theorem is attributed to Napoleon Bonaparte, even if it's probably not true that he proved that theorem. Maybe it's a friend of him, Mascheroni, who proved that theorem. Anyway, this is somewhat famous theorem, and there is another one. So this is, I would call that the first Napoleon point, but there is a second Napoleon point where you take equilateral triangles pointing inward inside the triangle ABC and not outwards. So there are two Napoleon points, and there is also the Fermat point. The Fermat point is in fact simpler to define because you just consider the lines joining a vertex like C and the opposite vertex of the equilateral triangle like gamma. So you consider C gamma, B beta, and A alpha, and these three lines meet at some point, which is called the Fermat point. So how can we prove that the Fermat lines or the Napoleon lines are concurrent using our technology of two functions? Well, let's try first the Fermat points because it's a little bit simpler. And here we will use complex coordinates. They are quite handy for this computation. So we would like to find the complex equation of the line joining C and gamma. For this, we need the complex coordinate of gamma, and it's simple to obtain thanks to the fact that gamma is the image of A by the rotation with center B and angle pi over 3. Using this, then you easily see that Z gamma minus ZB, which is the complex coordinate of the vector B gamma, is equal to to the y pi over 3, exponential y pi over 3, times the coordinates of the vector BA, which is ZA minus ZB. Using this, you can solve for Z gamma, and using this notation, W equals exponential of y of I pi over 3, we obtain a more symmetrical equation for Z gamma. Now we have the complex coordinate of Z gamma, and using the complex coordinate of C, it's a simple matter to obtain the complex equation of this line. And I just give you the result, which is here, and to obtain it, you just use the fact that if M is a point on this line, then the complex coordinate Z of M will satisfy the Z minus ZC over Z gamma over ZC is a real number. And using this, you obtain easily this equation. Now you insert Z gamma, given by equation 3, inside the left-hand side of this equation, and you obtain that the left-hand side of this equation has this form, which is some complex number minus CC, meaning its complex conjugate. So this is a pure imaginary complex number, so I can write it like this: I times some function of the point M, whose complex coordinate is Z. So we now, this defines a function f a b c of M, which turns out to be a two function. Well, the map ABC maps to FABC is a two function, because of course the zero set is a line. This is the line, this is the Fermat line that we consider. Now we would like to know if this two function is cyclic. For this, we sum over cyclic permutation, and we obtain something like this, factorizing by z. We have here an expression which is the sum over all cyclic permutation of the letters ABC times z, plus something I call t, which is the sum over all cyclic permutation of this guy, minus the complex conjugate of the whole thing. And it turns out that S has the form W bar plus W minus 1 times ZA plus ZB plus ZC, which is equal to 0, because you can remember that W is exponential of I pi over 3, so W it has a real part which is equal to 1/2. So this is equal to 0. Hence S is equal to 0. T is not equal to 0, but you can observe that T is a real number because this guy is the complex conjugate of this guy. So T will cancel out with its complex conjugate. So indeed, F will be a cyclic two function. So we know that the Fermat lines will be concurrent by our trivial lemma number 1. And we can observe that this works just because of this fact: W plus W bar equals 1, which allows us to make S vanish. So this is the only condition we need. So we don't really need that W is exactly the exponential of y times I times pi over 3. In fact, you can replace W with any complex number with real part 1/2. So any complex number of this form, 1/2 plus IY, with y any real number. And if you do that, then the complex coordinate of gamma will become the complex coordinate of another point, which I call gamma y, and this coordinate is ZA plus ZB over 2 plus IY ZA minus ZB. But now we observe that ZA plus ZB over 2 is just the complex coordinate of the midpoint of AB, and here we have the complex coordinate of the vector BA, which we multiply by I, meaning that we rotate it by pi over 2. So this parameterizes a line which is just the perpendicular bisector of the side AB. So what this tells us is that for each value of y, we will obtain a certain point on the perpendicular bisector of AB, and joining these points with the opposite vertex, we obtain 3 concurrent lines. So for instance, if you take y equals square root of 3 over 2, we obtain here, this is the case we started from, so this is exponential I pi over 3, so this point here will be equal to z gamma. So in that case, we recover the Fermat line. But if we take y equals plus square root of 3 over 6, it's easy to see that we obtain the centroid. This point here, this complex number here is the complex coordinates of the centroid, and so we obtain the first Napoléon line. And if we take a minus square root of 3 over 6, we obtain the other Napoléon, the second Napoléon line. And if we take y equals 0, and then, well, we obtain here just the midpoint, so the line will be the median. And we also know that the median are concurrent. We already know that, but here we recover that fact in quite a convoluted way. But what we obtain is much more, is that we have an infinite number of families of concurrent lines, which are, let's say, cousins to the Fermat and Napoléon and median, like they are all in one big family. So we obtain that theorem, which is that if we let gamma y to be the point on the perpendicular bisector of AB lying at a distance modulus of y times AB from the midpoint A prime towards the exterior or towards the interior of the triangle according to the sine of y, then the line joining C and gamma y and the other lines obtained by cyclic permutation are concurrent. And this theorem generalizes at the same time the fact that the medians are concurrent, the fact that the Fermat lines are concurrent, and the fact that the 2 Napoléon lines are concurrent. So this is nice, but now we can wonder why this works. Why does it work? Well, it might be a little bit disappointing here, because the reason it works is quite simple. In fact, it just has to do with some determinant. Let's explain that. If we take 3 distinct lines with equations of this form, where I is 1, 2, or 3, we can either consider the Cartesian equations and using the Cartesian coordinates, or we can also use barycentric coordinates for that matter. The result is the same, and the result is that these lines are concurrent or parallel if and only if this determinant is equal to 0. It's quite a well-known result. We can find the proof easily on the web, and if you like, you can also use my book, which will be out in September, I think. That is, if you speak French. But now, what does it mean? Well, it means that these 3 vectors in R3 are linearly dependent, and since they do not vanish, because this is a line equation, so all these coefficients are not vanishing, and also we have assumed that these lines are not the same, they are different lines. Then there exists a linear dependency relation with non-vanishing coefficients, and we can call these functions here are just the left-hand side of the equations of the lines. We can call them fi, so f1, f2, f3, and we have a linear dependency relation between these functions. But now we can redefine these functions by absorbing the coefficient alpha I. It's true that this a line doesn't have a unique equation, so you can multiply this equation by the coefficient you like, and if you multiply by the correct equations, the correct factor, then all the coefficient alpha here will be equal to 1. So, to sum up, if you start with 3 lines in a triangle, which I call A, B, C, and so on, and these lines are concurrent, then you consider the equations of this line. Let's say the equations in barycentric coordinates, and multiplying this equation by the correct factor, you will obtain a cyclic property. So you will be able to define a 2 function in an ad hoc way. So in a way, the cyclic trick we have talked about always works. But it's not always a natural thing to do, because you have to choose the correct normalization factor. And I tried, for instance, on the splitters, on the cleavers, which are other families of concurrent lines, and the coefficients is not really difficult to find, but it's quite it's not very natural. You do it in order that it works. So it's not like in the Fermat case. In the Fermat case, we just did exactly what was natural to do, and we obtain immediately a cyclic to function. We did not have to tinker anything. So what I'm saying here is that with some amount of tinkering, you can always use 2 functions, cyclic 2 functions, to prove that lines in a triangle are concurrent, just because of this result concerning determinant. But this raises another question. I say this is not always natural, but what do I mean by that? What does natural mean? So, what would be a natural 2 function? So, let's first consider a triangle, and we can, on this triangle, we can use some similarity, for instance, a rotation. And if we rotate it, and if we take a line which has a geometric meaning, for instance, the median, then the median will be rotated along with the triangle. This is a property which has a name which might be a little bit frightening, but it's not really difficult, because it's just what I have explained here on this picture. The name is equivariance. We say that the line that we have defined is equivariant. And this means the following: the line on the triangle SA, SB, SC, which is this triangle, is S of the line we had in the original triangle. So it's exactly like this. The median, if I consider the case of the median is rotating along the triangle, and I can use a rotation or any similarity for that matter. And this is exactly what is meant by equivariance. Equivariance means that the line is transformed along the triangle at the same time. So I think we can all agree that a natural set of lines will be an equivariant set of lines in a triangle. I will not consider a random line, but I will consider a line which is defined thanks to some geometric property, and thanks to this it will be equivariant. So the two functions we have to use will also have to satisfy this property. But in order for the line corresponding to the function to be equivariant, we do not necessarily need the function itself to be equivariant. We can, of course, if we ask the function to be equivariant, that is f of SA, SB, SC equals f ABC composed with the inverse of S, then if we ask for the equivariance of f, we will obtain the equivariance of the line it defines. But it's maybe a too strong requirement because we can as well multiply the function by some real factor, non-zero real factor. And this non-zero real factor, which I call lambda s, will have to satisfy some property with respect to the composition of similarities, and this property is just that lambda must be a group homomorphism from the group of similarities to the non-zero real numbers. It turns out that we can easily classify the homomorphisms from the group of similarities into the real, and these homomorphisms are just either the modulus of the determinant to some power, or the same thing multiplied by the sign of the determinant. For instance, if I consider the two function f a b c of m is equal to determinant of vector ab and vector cm, then if you compose by some similarity, then you will obtain SA, SB, and which is the same as the vector S, the image by S of the vector AB, and it's a very well-known property of the determinant that determinant of S will factorize, so here lambda will be exactly the determinant. So this is what we mean by equivariance. So equivariance of lines, and as far as two functions are concerned, we can add this factor, and we will call that property twisted equivariance. So now we are in a position where we can try to prove some fairly general results. First, we can prove results about equivariant line distributions. So we will assume that L is a distribution of line in triangles, which is symmetric, meaning that LABC equals LBAC. It's a natural assumption to make because, well, it's satisfied in every case we have already met. For instance, the altitude from C is the same, is the perpendicular line through C, perpendicular to AB, but it's exactly the same as the perpendicular line through C, perpendicular to BA. So the line distribution, if you consider the altitudes, the angle bisector, and so on, and even the Fermat lines, they are all symmetric. So we make that assumption, and we also ask for equivariance because this is the sensible thing to do, and we ask them to be concurrent because that's what we are interested in. And the first proposition we can prove is that if ABC is an isosceles triangle at C, then LABC is either parallel or perpendicular to the perpendicular bisector of AB. The proof is quite simple. I leave it to you. If you want the proof, you just You just read it here. But if you don't want to spoil your fun, then don't read that and try to do it yourself. Then we can use this proposition on an equilateral triangle, and here we find that the three lines must be either the perpendicular bisectors or the lines which are perpendicular to them, to these bisectors, passing through the centroid. That is, the second case is just the three perpendicular bisectors, and you rotate them by pi over 2. Here again, I leave you the proof to read if you like, but you're welcome to prove it yourself. And then we can also prove using a construction which is the one we have already seen in the Fermat and Napoléon theorem. If we construct equilateral triangles on the sides of any triangle, then we can prove that if LABC is a distribution which is independent of C, independent from C, then LABC must be the perpendicular bisector of AB. So there is a single distribution of line which have these three properties and is independent of C. So that's simple, but that's already a general result. Another result we can prove is a result that singles out the medians. The medians have a particular property because in that case the distribution is equivariant not only with respect to similarities, which is what I assumed here. The equivariance is with respect to the similarity group. But if you require the stronger property that L is equivalent with respect to every affine transformation, then LABC has to be the median from C. And this follows from proposition 2, because you can always transform any triangle into an equilateral triangle using an affine transformation. So the medians, and it's quite and it's clear because the medians depend on the midpoints, and the midpoint is an affine notion, whereas the perpendicular bisectors, the altitude, etc., the definition of these lines use metric notions like angles and distances. So now let's turn to two functions. We have proven some general results about distribution of lines, but now we would like to prove a general result concerning two functions. So what can we ask? What can we be interested in? Well, we can consider exact two functions. We can interest ourselves into these two functions, those which are exact. And so we look for a two function which comes from a function depending on 2 points, which I would call a one function. And we want this one function g to be symmetric in AB, twisted equivariance in order for delta g, so the exact two function will be delta g, and we want it to be twisted equivariant, so we ask that g is, and we of course want that the zero set of delta g is a line. With these assumptions, I recall that delta g will be cyclic, and so we'll define concurrent lines. So if g has these properties, then it's easy to see that GAB of M can only depend on the metric quantities which are defined by the triangle ABM. And these quantities are the length of the sides AM, AB, and BM, or equivalently you can also use the angle. Well, in the angle you have an additional information because you have an orientation, but twisted equivariance means that if you compose by the reflection about the line AB, then JB of M and JB of the symmetric of M with respect to AB, it's either the same thing or minus the same result. So we have two cases, and I will just consider the case where we have a plus here. So we will ask that GAB depends only on AB, AM, and the angle, but the non-oriented angle, so the absolute value of alpha. And it's equivalent to to require that GAB depends only, JB of M depends only on AM, BM, and AB, because the three sides of the triangle allow you to recover all the information that you have. But since it is symmetric, it has to be symmetric, AM and BM must enter the definition of GAB in the same way. So we will assume a general form for GAB which satisfy all these requirements, and it will be GAB of M is given by some second degree homogeneous second degree polynomial on AM, BM, and AB, which is symmetrical in AM and BM. So maybe you are saying that, okay, now this is not general anymore because we have made an additional assumption that G is given by a second degree polynomial. But in fact, this assumption is here to ensure the third property, that delta G, the zero set of delta G, is a line. Because if you use a third degree of any polynomial in some other degree than 2, you don't have this property, sorry. So, okay, I do not claim to have a proof of that. I haven't worked that out, but you are free to do. You're welcome to do it if you like. But I think that this is fairly general. So I'm not claiming that this is the only function that can satisfy these three requirements and the additional plus sign here. But I think we are not too far from that, from complete generality. So now we compute delta G ABC of M, and it's GAC of M minus GBC of M, which is as this form, and we recognize here an identity which allows us to factorize by the vector AB. And using a trick which is very elementary, introducing the midpoint C prime, we can obtain the following form. So it's 2AB dot x C prime M plus y C prime C. So the zero set of delta G is a line because this vanishes for the points M which belong to a line which is perpendicular to AB and which goes through the point here which I will call M0, which belongs to AB and satisfies this dot product equals 0. And you can work this point M0 out easily, and you find that using Charles relations that AM0 is equal to AC prime minus K C prime HC, where I called K the only parameter which enters this thing, which is y over x, and I called HC the orthogonal projection of the vertex C on AB, on the line AB. So let's consider some examples. If y equals 0, so k equals 0, we see that M0 is C prime, so that LABC is the line perpendicular to AB passing through the midpoint of AB, and that is the perpendicular bisector. Another case we can consider is that if y equals minus x, so k equals minus 1, and here we see that M0 equals hc, so that we recover the altitude. So, what have we obtained? Well, we have obtained that delta G is in fact a two function, and it's necessarily cyclic because G is symmetric, and so we have a whole family of concurrent lines which depend on the parameter k, and when k equals 0 we recover and when k equals minus 1 we recover two well-known families of concurrent lines coming from exact two functions, and we already knew them. But what about the others? Well, to see what the others are, let's solve for the coordinates at the meeting points of the three concurrent lines LABC and so on. So this meeting point, let's call it X, it will belong to LABC and also to LBCA, so it will cancel this scalar product. Here M, you replace M by X, so you obtain the first equation, and you obtain also a second equation using BCA instead of ABC. So you have two equations, and you obtain a system of linear equations which you can solve using Cramer formulae, for instance, and you see that the solutions depend on K in a linear way, because you can put this scalar product AB times C prime C on the other side, and you see that it depends linearly on K. So it means that the meeting point moves on a line because its coordinates are given by a first-degree polynomial in the parameter K. So we have obtained a line which goes through the circumcenter and also through the orthocenter. But we know that line. It is the Euler line. The Euler line is well known. It's a line which goes through many interesting centers in a triangle, in particular the circumcenter, the orthocenter, and the centroid. And we recovered that fact here, and you can see that the centroid is obtained in our case with the parameter k equals minus 1/3. But we obtain much more. We obtain that the Euler line, in fact, every point in the Euler line is a center, in the sense that it's the intersection point, the meeting point of a family of three equivariant lines given by exact two functions. And in fact, I admittedly did not give a complete proof that every point in the Euler line, well, let me say that again. Every point in the Euler line corresponds to an exact two functions. I proved that. But conversely, I did not prove that every exact two function corresponds to a point on the Euler line, because I made some additional assumptions, like second degree for the form of GAB and so on. But I think that it's not very far from it. So at least we have an interesting result that a very classical and famous line in fact shows up naturally in our setup of exact two functions. So now let me conclude by saying that this study of concurrent lines in a triangle has shown a somewhat general trend, and it is that it is not always possible to generalize a beautiful proof like the proof by Gauss that the altitudes are concurrent, because such geometric proofs generally use something like a shortcut, whereas the algebraic proof may look a little bit more clumsy. Certainly, they are not as neat, but they allow us to build a sort of highway that we can drive in to prove other results, and so that's a kind of geometry versus algebra debate. But I should say that we shouldn't see that as an opposition. It's rather a synergy, because these two branches of mathematics in fact go together, because for a very simple reason that we wouldn't have had the idea without the geometric construction first. So geometry will give us motivation and will also give us insight. But the algebraic approach will allow us to gather cases into families, and also to easily rediscover subtle geometric results, like the existence of the Euler line, or the Fermat or Napoléon lines. It also suggests new questions, more abstract questions, like the classification of twisted equivalent exact two functions, which I started in this video, and that maybe I will finish that in some future, but you are welcome to try it yourself if you like. And well, that's it. And I hope that you have enjoyed it, and don't forget to check out the links in the description, in particular to some proofs that I had not the time to give in details. And also, if you like the videos, you can subscribe in order to be informed of future updates. See you soon for another video.